Okay, so do you have any question from our last session? Because we kind of made a mistake and then we ran out of time, so I solved that problem in kind of hurry. No questions? There was one more problem in our last week's discussion, and I believe we need to solve that before we solve the questions that we have for today. And the reason is that problem was related to conservation of momentum. And our first problem today in this worksheet, it's related to conservation of momentum. This is more of a theoretical understanding question, and the question that we had in our last week's discussion pack, that was a bit of mathematical. And it's better to understand the mathematical part first before going on to answer any conceptual theoretical kind of problem. Okay, so the question that was in our last week's discussion, it was the last question, and its statement is Dan is gliding on his skateboard at 4 meters per second. This is from last week, that's why I'm gonna read the statement to you if you don't have the copies. And he suddenly jumps backward off the skateboard, kicking the skateboard forward at 8 meters per second. How fast is Dan going as his feet hit the ground? Dan's mass is 50 kilograms and the skateboard mass has skateboard has a mass of 5 kilograms. So this was last week's problem. So let me make a rough diagram for this. So we have two objects, Dan and his skateboard. And initially Dan is gliding on the skateboard at a speed of 5 meters per second. So let's choose the direction of motion. It has not been stated in this problem that in which direction Dan is moving. So that's purely our choice, that we decide in which direction Dan is moving. And so let's pick this rightward direction. So we have a skateboard and we have a Dan on it, and they are both moving in this direction, and their combined speed is, let me call it VI, and this is 5 meters per second. Okay, so at some point Dan jumps in the backward direction, and as he does so, the skateboard moves forward alone with a speed of 8 meters per second. So the second situation is we have the skateboard moving alone. Let's call it Vs, and this is 8 meters per second. And Dan moves forward with some speed. Let's call it Dan. And I'm constantly using the word speed. That's because I have fixed my direction of motion. So I have decided that the Dan and the skateboard, they are moving in the right direction. So since I have fixed the direction, now I can use the word speed for velocity, which means I'm just talking about the magnitude. Okay, so this is the situation. We are supposed to calculate this speed with which the Dan moves in the backward direction. Okay, this problem is related to conservation of energy, conservation of momentum. And conservation of momentum demands that the total initial momentum, that's like P initial, and this is total, this should be equal to P final total. Okay, I'm using the word total because there can be more than one objects in your system, and so your total momentum would be the sum of momenta of all the objects involved. So we have two objects in the first case, and they are moving with some combined speed 5 meters per second, and the objects are Dan and his skateboard. Okay, so in order to find the total initial momentum, we have the definition of momentum as mass times velocity. Okay, so in this case the mass is a sum of mass of skateboard and mass of Dan. That's the total mass, and they are moving with some combined speed, which I have represented by a symbol VI, and so this is the situation. Mass of skateboard is 5 kilograms, mass of Dan is 50 kilograms, and so the total mass is 55 kilograms multiplied by the total speed, and that is 5 meters per second. Okay, and so we get the total initial momentum. This would be 250 plus 25, 275. Okay, so the total initial momentum is 275 kilograms kilograms meters per second. That's the total initial momentum. In order to use this relation, we also need total final momentum, and if we calculate the total final momentum, which is P final total. Now, if we look at this situation, skateboard is moving at its own with a different speed than the Dan. So now we don't have this kind of situation in which I added the total mass. Now we have two different objects moving with possibly two different speeds. And so now I have to write mass of Dan times speed of Dan plus mass of skateboard times speed of skateboard. Okay, this will give me the total final momentum. Dan's mass is 55 kilograms, so this will be 55 times Vd, because this is the velocity or speed that we want to find. And then we have for skateboard, mass of skateboard is 5 kilograms and its speed is 8 meters per second in this case. So we have this situation. Okay, here we need to take care of the sign, and that's why I wanted to solve this problem first, because this is important. So I decided that this system, like the skateboard and the Dan, they are moving towards right. Okay, and I took their speed to be positive. That's what I have used here. It's plus 5. Okay, that means that I have decided that the right direction is positive direction of motion. That the velocity in this direction is positive, and anything, if it moves in the backward direction, it should have a negative value. Okay, and in this situation, in the final situation, we see that the Dan is moving in the backward direction. So in order to find the speed of Dan, I need to include a negative sign here with Vd. And so this Vd is actually minus Vd, and that sign will show up here. You can put it here too if you want. Okay, so this is our final momentum. And you need to take care of this thing from this thing that we have decided in start. When I start solving this problem, I mentioned that the problem does not state that in which direction Dan is moving. It just states that it's moving at a speed of 5 meters per second on his skateboard. But there was no mention of direction, so which means that we had the choice to choose the direction of motion. And I chose that they are moving towards right. And if they're moving towards right and I took their speed to be 5 meters per second, it means that the positive, the right hand side, the motion towards right gives me the positive value of velocity. It means anything which moves towards left will have a negative value. And so we saw that after, in the final scenario, the Dan was moving in the backward direction. And so I have to put negative sign with the speed of Dan by hand, because I know which convention I chose. Okay, so you have to use a negative sign here. And now I can use this relation, total initial momentum equals total final momentum, and initial momentum was 275. So this was 275 kilograms meter per second, and this should be equal to 50 minus 55 times Vd plus 40, and this right hand side also has the units of kilograms meters per second. Okay, so I bring this 40 to the left hand side, and if I do that, this will become 235, and this will be equal to minus 55 Vd. Okay, and if you find Vd from here, this will turns out to be minus 3.6 kilograms meters per second. Okay, this is the Dan's final speed. So this is the speed. Can somebody explain the negative sign? Why we have a negative sign here with the Dan's final speed? Anybody? Yes.
It's because Vs is going 8 meters per second positively to the right, so
yes.
for it
yes.
to Vd has to be negative.
Yes,
so it's
yes, that's perfect. Okay, just remember that while studying physics, whenever there is a negative sign, which you do not understand that from where this showed up in my calculation, just look for whether the quantity that you are trying to calculate is a vector quantity or a scalar quantity. Okay, just remember that velocity is a vector quantity. It means you have to fix its direction, like which way it is positive, and if it's pointed in the other direction to the direction that you have chosen as positive, its value should be negative. And since I chose my rightward motion to be positive, it means anything that moves in the left direction should have a negative value, and that's this negative sign which will pop up in my calculation, which means mathematics doesn't lie. You just have to come up with a reason that your mathematical answer makes sense. Okay, so also let me take a look at my calculations, because I remember the answer but I'm not sure about the calculations. Anyway, so in the question, the initial speed is 4 meters per second. I took 5 meters per second. The rest is fine. So just replace this with 4. That's why I was not sure that it's right. So this will be 4, this will be 4, this will become 220. And now this side will be 220. And then this 220 minus 40 will be 180. And now your answer will be 3.6. Doesn't really matter. You got the idea how to solve questions which involve conservation of momentum. Now we can peacefully move towards our first question in today's discussion pack. And now I hope you can answer me. Somebody came late who didn't have these, and anyone else? No? 2. Okay. So now can you tell me what should be the answer to the first part of first question? It's just conservation of momentum. You have to use that idea. Anyone? What's the answer to this first part? Two particles collide, one of which was initially moving and the other one was initially at rest. Is it possible for both particles to be at rest after the collision? Give an example in which this happens, or explain why it can't happen. It's a simple one. So initially you have two particles, and one of them is at rest and the other one is moving with some speed. And that particle which is in motion, it collides with the other particle which is at rest. The question asks, is it possible that after the collision both particles ended up being in a state of rest? Is it possible? I want somebody else to answer me. Thank you. Why it's not possible? I saw some heads shaking in negation. Why? It's a simple argument. Come on, give me that. We've just talked about it. Yes, Amit.
Is it because the momentum of the ball that hits the one that's stationary?
Yes.
That
Yes.
momentum will carry forward
Yes.
that one?
That's perfect. Right? So just remember that this law, it's a very strong law, this one, the conservation of momentum. Okay? You cannot just violate it. There's no phenomena happening in nature in which you see the violation of this law. Such kind of laws, we call them universal laws. They are valid at any point in the world we live in. Okay? And this law tells you that the total initial momentum should be equal to total final momentum. Now just look at the statement of the problem. It demands that the total final momentum of the two particles is 0, because it is asking that whether the two particles are at rest or not. Okay? So the total final momentum is 0, but initially it is explicitly telling us that one of the particles is in motion. If one of the particles is in motion, it means you have some non-zero momentum in the initial state. Although the second particle is at rest, but if one of them is moving, its momentum is non-zero, and so the total initial momentum will be non-zero. So total final momentum can never be 0, so it's not possible. The second part of this question asks, can you think of a situation in which this happens? That the total final momentum turns out to be 0. Is it possible? Can you think of a situation when it's very easy, it's still on the board, same equation? Okay, go ahead.
When two cars like go head to head in
Yes,
contact.
yes. So you see, if we have here two particles, okay, and total momentum should be their sum. So total momentum here, P initial total, it's the sum of momenta of two particles. Okay, let's say the particles have masses m1 and m2, and their speeds are, initial speeds are v1 and v2. Okay, so we are not worried about how they are moving initially. The only thing that we care about is that this thing should be zero, which means we are demanding that the right hand side should be zero. Okay, masses, they are scalar quantities, positive numbers, but the other quantities, the velocities, they are vectors, which means they can take positive value or they can take negative values. Okay, so how come you can make this equation, right hand side of this equation, zero? Let's say if v1 has a positive value, then the condition that you are looking for, that v2 should have the same value as v1, but the direction should be opposite, which means with a negative sign. And if you do that, your total momentum, total initial momentum is zero. And that's it. If your total initial momentum is zero, the question asks, your total final momentum should be zero. And this happens only if the two objects, let's say this is the first object with mass m1, if it is moving with speed v1 towards right, then we see that we have a second object, mass m2, and it is moving with speed v2 towards left. Okay, and then the condition that I'm demanding is that m1 equals m2 and v1 equals minus v2. That's it. Total initial momentum will be zero. Okay, this is not the only condition that you can use to make total initial momentum zero. You can choose m1 and m2. For example, if I say, let's say m1 is not equal to m2, still you can adjust speeds in such a way that the sum should be zero. This is one condition in which you get the initial momentum zero. Okay, so you can come up with other values too. The only thing that you are looking for is that you make the total initial momentum zero. And you can come up with many ways in which you make the total initial momentum zero. So yes, there is a situation in which the final momentum of the objects will be zero. And one of that situation you can attain by this condition, that the objects have the same masses and they have the same speeds, but they are moving in opposite direction. Okay, which means they will collide, and after collision they immediately comes to rest. Okay. Okay, second part of this question is it possible for one particle to be at rest after the collision? Give an example in which this happens, or explain why it can't happen. Is it possible that one of the particles after the collision comes to rest? Yes. It's a little tricky one, but yes, of course. You want to explain it? Why?
Basically what he said again, just
Yeah.
the collision or momentum transfers.
Yes. Okay, so initially if you see that, thank you. Initially if you see you have a particle, let's say any mass, okay, and it's at rest. And you have another particle moving towards it, and since it's moving, let's say its speed is v1, mass is m1, and so it has some momentum. Okay, so collision happens, and we are only looking for one thing, that one of these two particles should end up at rest. And now we see that if a collision happens, this is definitely gonna move from its place. And so if this moves, we want this to be at rest. How can this to be at rest? If somehow it gives all of its momentum to this particle, which means that it will have now zero final momentum, so it will immediately come to rest, and this particle will start moving with the momentum which is equal to the momentum of this particle. So this is the second condition. Okay. The second question is related to energy, and we have three situations, and we want to plot kinetic energy against time, like how the kinetic energy of an object, which in this case is car, it changes with time, and you have to draw a graph for this system. We have three situations, and the object is not moving with a constant speed, it's moving with a constant acceleration. Constant acceleration means the speed of the object increases with time. So your answer will not be a straight line. So all three graphs, they are somewhat like this. So you have vertical axis, you have horizontal axis, you have time on the horizontal axis, you have kinetic energy on the vertical axis. Some values, we don't worry about that, you can look them up in that worksheet. And so then we have second situation, again time, kinetic energy, and then we have third situation, time, kinetic energy. Okay, so object is moving with some constant acceleration such that it attains a final speed of 20 meters per second in 20 seconds. Okay, so it starts from rest, and in 20 seconds it attains a speed of 20 meters per second. Okay, now from the definition of acceleration, you know that acceleration is velocity or speed divided by time, and it attains a speed of 20 meters per second in 20 seconds. Okay, and so your answers turns out to be, acceleration turns out to be 1 meter per second square. Okay, so it's accelerating at an acceleration of 1 meters per second. So now you can calculate kinetic energy. Kinetic energy, you know the formula, it's a half mass of the object times its velocity squared. And from here you can see velocity is acceleration multiplied by time, and so this becomes half mass times acceleration times time squared, and we have just calculated accelerations to be 1 meter per second. And if acceleration is 1 meter per second, it means you can just write kinetic energy in terms of, time, which will be half m times t square, because acceleration is 1. So if you substitute 1 in this equation, you get the that formula. Okay, and now you have an interval of 5 second, 10 second, 15 second, and 20, and so you have similarly 4 intervals of kinetic energy on the vertical axis. So in that equation, now you can use t equals 0. At t equals 0, your kinetic energy is 0. So this is the point of 0 time and 0 kinetic energy for the first case. If you use t equals 5 seconds, so this equation becomes half, and mass of the car is 1000 kilograms. If you use t equals 5 seconds, this is gonna be 25, and 500 multiplied by 25, 25 times 5 is 125, and then we will have 2 zeros because that's 500. Okay, so you find a value of 125, 12,500 joule on the vertical axis, turns out to be somewhere here, and so your second point, which corresponds to t equals 5 seconds, will be here. Similarly, you use t equals 10 seconds, you find the kinetic energy at that point, and then you get the second point. Then you get the third point, and then you finally get the fourth point. And fourth point, like for t equals 20 seconds, your kinetic energy turns out to be 200,000. Okay, that's the maximum, corresponds to this value. And so your graph would be somewhat like this. Okay, it will not be a straight line, it will be a tilted one. Okay, so this is not to scale, which means I have not drawn it precisely. How do you draw the precise plot? You find the 12 for t equals 5 seconds, it's 12,500 joule. Then you use t equals 10, calculate the other energy, and you get the second point. Then you use t equals 15, corresponds to this point. You get the energy and make a point there, and then you connect all those dots. It will not be a straight line. This is the first part in which the car starts from rest. Okay, the second part, the second graph, it says that if the car is initially moving with a speed of 20 meters per second and it comes to rest in 20 seconds, then plot the graph. So that the second question is just the inverse of this one. You see, it starts from rest, and in 20 seconds it gets the speed of 20 meters per second. The second problem asks, if it is initially moving with 20 meters per second and it comes to rest in 20 seconds, what will be the plot? It will be the totally reflection of this. Okay, which means that now it starts at 200,000 joule, which is the energy after 20 seconds. Okay, so it initially moving with this speed, and now your curve would be somewhat like this. This corresponds to t equals 20 seconds. Okay, so it's just the reverse of this curve. So after 5 seconds, t equals 5 seconds, its energy would be what you get for t equals 15 seconds for the first case. For t equals 10, its energy will be same. For example, if I use t equals 10 in this one, kinetic energy would be half 1000 multiplied by 100, which is 10 squared, and this will become what will it become? 500. So 500 and 2 more zeros, joule. Okay, so this is the kinetic energy at t equals 10 seconds. So this will be the same. This is this energy. How much is it? 500 joule. Okay, and then similarly you can calculate for t equals 15. So these two graphs are just reverse of each other. And the third one, I want you to answer me for this one. And in this case, the car is moving in a circle which has a diameter of 130 meters and its speed is constant, 20 meters per second. How would the kinetic energy graph look if its speed is constant? How would the graph be? Would it be a curved line like these two cases, or it will be a straight line? It's just moving at a uniform speed in a circle, which means its speed is not changing with time. Look at the formula for kinetic energy here. In first two cases, V was not fixed, okay, and so we used V equals AT. But in the third case, V is fixed. There is no time dependence. Its speed is fixed at all times. And if speed is fixed, it means we use this formula for kinetic energy. And this formula gives us one value, which we have already calculated, 200,000 joules. If I use V equals 20, this is the energy that I get. Okay, so the third case, in this case, we will have a straight line, which means that the kinetic energy of the car is fixed and it's 200,000 joule. That's it. That's a straight line. So these three cases are different. In these two cases, the speed was not fixed. It was changing. It was, in this case, it was increasing with time. In this case, it was decreasing with time. And in this case, speed is constant. So it's fixed. It's independent of time. And if it's independent of time, you should get a straight line. Okay, a fixed energy. This last problem, it's related to gravitational potential energy. It's important. One important thing is that you always measure the gravitational potential energy with respect to some reference point. And this question is purely related to that reference point. So you have a situation described in the problem. You have a ball. So you have height. You have a ball here initially at height of, this is height. So this is 1 meter, this is 2 meter, this is 0. So 0, 1, 2, we have height in meters. Okay, and then we have 3 observers. Their names are Anjay, Brittany, and Carlos. Okay, and they have different reference points, which means that they measure the potential energy for this ball with respect to different reference points. Okay, so okay, this is a very bad copy. Anjay's reference point is this one. So Anjay measures the energy of the ball with reference to this point, which means that Anjay thinks that the zero of potential energy lies here. And the formula for potential energy is U equals mgh. Okay, and if the ball is initially at this point and Anjay's reference point is this line, it means that with respect to Anjay, the ball is at a height of 1 meter. And so the initial energy, potential energy with respect to Anjay will be mg times h, which is 1. So its initial potential energy will be mg. And its final energy, she takes the ball from this point to this point, and its final energy, uf on j, will be 2 times mg. Why? Because when measured from this reference point and the ball ends up here, the height is 2 meters, and so if we substitute h equals 2, so we get 2 mg. So for J, the difference in potential energy delta U for J will be H2. This one final minus initial, this turns out to be mg. Okay, this was for J. Now we need to calculate for Brittany, and for UI Brittany, and the reference point of Brittany is this line. This line is the reference point of Brittany, which means that on this line the potential energy with respect to Brittany is 0, and the ball lies on this line, which means that the initial potential energy with respect to Brittany will be 0, and then Brittany moves this ball from this place to this place, and we have a distance of 1 meter between these two lines. And so if I use h equals 1 meter in this formula, the final potential energy for Brittany will be mg. And if you calculate the difference, this will be mg final minus initial. Okay, and finally we have Carlos. For Carlos, this is the reference point. Okay, if this is the reference point, initial position of the ball is 1 meter below his reference point, which means height is negative in this case. Okay, so you in this formula you use h equals -1, and so for u initial Carlos, this will be minus mg. Final, he brings it to this point, which according to Carlos is 0. So final potential energy will be 0, and if you find the difference, which is final minus initial for Carlos, this turns out to be mg. And if you look at this line, for these three cases, you see an important similarity arising out of this. That although they measure different values of potential energies at each point, the difference of potential energy is the same for all three of them. Okay, this tells you that the physical quantity, the relevant quantity which you can measure, is difference of potential energy, not the potential energy at any particular point. And that is because the reference point, it's purely our choice. So potential energy at any particular point, it does not depend on the reference point. I can choose one reference point, you can choose another reference point, as we have seen in this situation. But the thing that is physically important and relevant, that's the difference of potential energy, which means that if you take this ball from one point to another point, then no matter who measures that potential energy and whichever reference point that person chooses, if he takes the difference of potential energy, like the potential energy at the final point minus the potential energy at the initial point, he will always measure the same difference. Okay, so difference of potential energy is important and physical, not the potential energy at any particular point. Okay, questions? No? Good, that we are almost out of time. Thank you.